Okay. Well, I got some public speaking advice from Aaron Dean a while back, and he said, always be the smartest person in the room. But if that's not possible, at least be the best dressed. So I think I'm compensating pretty well today. I know everybody online can't see me, but I want to thank IEDD for giving us all an excuse to put pants on. So today I'm going to talk about a digital insight with an operator that I work with on a daily basis. But I think one thing that's a common theme of today is that data is everywhere. There's no denying we live in a world of data, but even when I started with the oil field 12 years ago, in-bit sensing was common. There were at least 2 companies that had it, and even more were coming out with the capabilities. But where have we gone since then? Well, there's certain challenges that face all of us. Some of the advancements were in-bit sensing technology. The sensors that have improved, battery life has improved, even data acquisition and management systems have improved over time. They've helped to improve the quality and quantity of data, as well as drive down the cost to deliver that service. But some of those costs cannot be avoided. If we're asking our field personnel to engage in data acquisition activities on top of their normal jobs of selling, running tools, or delivering products, then we're just stressing our human resources. Even asking an engineer such as myself to plot data from multiple sources takes time, and my time isn't cheap. So most organizations have, that's right. Most organizations have reacted to the downturn through massive layoffs. So those of us who are left are asked to show the value of the data that we've already collected. The case study I'm going to talk about today does just that, showing data from a single data insert that solves a specific customer problem. So the scenario I want to talk to you about today involves an operator in northern Louisiana that's trying to improve their Haynesville intermediate interval. This interval is typically drilled with 9 7/8 PDCs, usually 2 to 3 in this vertical tangent. As most of you know, the bottom of this interval is dictated by the Austin or Travis Peak and Cotton Valley, which are extremely abrasive and interbedded formations. So the operator decided to start with a 12 1/4 and take it down to the Rodessa at 5,000 feet as a contingency, and then they picked up our 9 7/8 RPS 616. Well, based on offset analysis, I thought that first bit was going to get to 8,500 feet. But I was surprised to learn that they pulled it early at about 8,000. So I asked the drilling engineer, why'd you pull our bit? And he said, well, I was seeing excessive stick slip. And I said, well, I don't really have that channel. What channel were you getting to tell you that? And he said the MWD was pulsing up values that equated to 200% stick slip. And I said, wow, that's really high, except the bit was pulled green. So there's something missing here. So we decided to reach out to our trusted partner in data acquisition services and put a sensor in the last run on the drill out, which is indicated by the, I guess, the last teal run over there. Can't really point with this. Anyway, so fortunately, we were able to drill to 8,500 feet after we agreed that we would continue to run it, even if we saw high stick slip values. And it ended up being the fastest drilling on the pad as well. Unfortunately, the dole came out a little bit worse than the first bit, but that was expected since it drilled deeper and more footage and was still repairable. So looking back at the first run, I decided to make sure that the engineer wasn't lying. And sure enough, I matched the stick slip index values, which come in the form of integers, with the guide that the directional company gave us. Apparently, everything is kind of in the order of every 50%, we get a higher number. And just to make sure we weren't misinterpreting the stick slip percent, they even attached the industry standard RPM range over 2 times the average. So basically what this equated to was massive backward rotation by something in the VHA, delivering that signal. So fast forward to the last drill out run, I was able to get the high resolution data from our service provider, and I was able to confirm that stick slip was in fact happening. If you look at the gyro RPM column, can't really point with this, but the minimum RPM, oh, there we go. The minimum RPM is touching the zero track a few times. The problem is the magnitude is nowhere near what the MWD was pulsing up. And we don't see any stick slip above this 8128 footage. And just looking at the stick slip column, that 0 to 100, there's no way we should be seeing 200%. So something was missing. So I reached out to the directional company and asked them for their high resolution memory-based data at the MWD. And I was able to plot the bit sensor RPM on the same depth as the MWD memory channel. So we're looking at RPM max, average, and minimum values. And one of the key takeaways is that the stick slip we noticed at the very end of the run coincided with a formation change into the Cotton Valley. So this was really eye-opening because we rarely see a surface parameter response based on just transitioning into the Cotton Valley. Even our RSA's rock strength analysis doesn't really show much of a difference. And gamma signature, you can't really tell either. So it's nice to know that our roadmaps are differentiating these two formations as to how we attack them. The other major takeaway is that the biggest difference between the bit and the MWD is the average RPM. This shouldn't be a surprise since the MWD is behind the motor, so it's not going to see the additional RPMs created by the motor. So by having a lower average, we see a lot of these values on the MWD go negative, which would be indicated by a high stick slip value, which is not seen by the bit. The bit seems to stay well above 0. In fact, most of the run is above 50 RPM, except for maybe the entrance into the Cotton Valley, which led to the other big takeaway is, well, the reason they pulled is because they were misinterpreting the MWD stick slip as bit stick slip. Well, we don't really care what the MWD is doing because it's not the weak point in the BHA. We really care about bit stick slip, but we don't have that channel. Well, then I thought to myself, you know, we collected a lot of data just with this run. I bet there's a way we can convert the MWD stick slip to read bit stick slip. So I went ahead and mapped out all the data we get from a normal run. So typically surface data is easy to come by as long as you have a login from the operator. The precision is really good, the frequency is really good. It just doesn't tell us what's going on downhole. MWD pulse data does tell us what's going on downhole, at least on the high side of the motor, and it's available in real time. We just don't get much precision out of it, and in this case, it was only pulsing up every 2 minutes. The MWD memory data is high precision and high frequency and tells us what is going on downhole, but still on this side of the motor. The bit is the final piece that gives us the explanation about what's going on on the other side of the motor, high precision and high frequency. So if we grab our typical equation for stick slip, I thought to myself, you know, this range, I bet we could figure out how to calculate that based on the relationship between MWD and bit sensor. The bottom part, bit RPM, we can figure out from surface data, and well, we already have a bit RPM. I bet we can figure that out too. So I started with the overlay. I did RPM max minus RPM min for both the bit sensor and the MWD, and lo and behold, they're almost a perfect match. This means that all the oscillation for the drill bit engaging that formation gets translated all the way past the motor, and that MWD sees every bit of vibration, even though it's at a lower average. So this made our equation really easy. We just solve for RPM max over RPM min for the MWD pulse value. And then we have to assume that the average RPM for the MWD is the same thing as top drive average. The next part of the equation is the bottom half, which is the RPM bit average. So a typical equation for that, we have our surface parameters of RPM top drive, flow rate, and motor speed. Well, we all know that motor speed is far from the nominal value, so we can't really take that as face value. And motor spec sheets do a poor job of providing us a formulaic alternative. Even their graphical measures aren't that good. So I decided to just solve for that equation since we already know bit RPM and see what that looks like. So this graphical representation shows us the relationship between motor rev per gallon and differential pressure. So it's a little scary, but most of those data points are below the nominal rev per gallon of high-speed motor, 0.17. and it tends to decrease as differential pressure increases. So we can take a simple linear regression model or a simple fixed percent of the nominal value and get a pretty close correction factor, which leaves us with our final equation for stick slip at the bit as a function of the MWD pulse data, our surface values for top drive RPM, flow rate, and this correction factor. So what does that look like if we apply it to a normal practice? Well, this is that same run, and in the red we have the bit stick slip, which is in percent. So the teal is our new calculation, which follows bit stick slip really well. In fact, even at the end when we get into the Cotton Valley, the bits showing percentages of over 100%, our new channel is right at 90%. I'd say that's pretty good considering the MWD pulse data we're being given it in integer values. So at the end of the day, we were able to solve a customer's problem with interpreting MWD data by reaching out to our directional company and making sure that we understood it fully. And then we provided the customer with an alternative based on the data that we collected. So the benefits of having this channel, well, now we can alter our top drive parameters to make sure that we can minimize stick slip and maximize ROP. It's going to help in pull point determination. We get real-time BHA component effects, and this can be used for their foreseeable drilling program. So let's say we have stick slip. Well, what do we do about it? Well, the easiest thing is going to be in surface parameters, which are usually an incremental improvement. But really, if we want to make a drastic improvement, we would just increase our drill pipe diameter. In this case, the operator is considering going from 5-inch to 5.5-inch, which often comes with a significant financial burden that has to be justified. So it's not an easy decision. But directional companies are always changing BHA components around, so it'd be nice to see what effect they have real time. And then lastly, for drill bit companies, what do we do about stick slip? Well, we just withstand it a little bit better, hopefully with features or cutter technology. But usually cutter improvements come in the form of incremental changes, which are often difficult to see in the DOL photos associated with so much variability in field testing. The last part of this project is communication. I feel like we became the trusted partner of the operator and service providers because we reached across company lines and interacted with key personnel in other organizations, most of which who have more data and insight that we lack, which helps everybody associated with the project do a better job. So data alone does not solve problems. It takes qualified individuals to make intelligent decisions based on that data and implement those learnings to the rest of the organization. I think that last part, everybody here would agree, is the most difficult. Carrying those learnings forward is one of the major responsibilities of IEDD, and I'm glad we're putting this event on today.